Let us now move to our second speaker, who is Dr. Monojit Choudhury. Dr. Choudhury is a principal researcher at Microsoft Research Lab India. His research interests include various subfields of NLP and its intersections with cognition, linguistics, and societal impact. Dr. Choudhury is an adjunct faculty in Plaksha University and IIIT Hyderabad. He is the general chair of the Panini Linguistics Olympiad and the founding co-chair of Asia Pacific Linguistics Olympiad. Today, he will be presenting his talk titled Applications and Techniques for CodeMixed Text Generation. Over to you, Dr. Monojit Choudhury.
Hi, am I audible?
Yeah.
Okay. And are these slides visible too?
Yes, yes.
Thank you, Vidisha. And thanks to the organizer for the invitation. What I'm going to talk today is very, very aligned to the theme, which is applications of data in AI and AI for data, right? Data for AI and AI for data. I think that's sort of the theme. So I thought I will talk about applications and techniques for generating code mixed data. And I'll in a moment come to why this is an important problem and what all we can achieve by doing that. Now, this all of you must be familiar with, that NLP has kind of gone through a revolution in the last 5 or so years. And especially just in the last 2-3 years, if you see, our models have grown really big, and not only big, also better. So GPT-3 is huge, and it's also an old news. Now we have bigger models than GPT-3. You would have heard about things like data is the new oil. Some people say it's the new electricity. And the side effect of all this is linguistic insights are no longer useful. It's kind of, nobody says it explicitly, but it's kind of everywhere. You talk to students during interviews, you talk to people in the industry. It's very apparent that nobody cares anymore about linguistic insights. But is it really so? Do we really don't need linguistic insights? And what I'm going to argue, and pretty much along the lines of Ido, what Ido said, that how linguistic information, structural information can really help even these giant models like BERT and all. So it will be similar kind of an argument, but applied to a very different settings. So what I'm going to argue is, when data, or let's say the oil, is scarce, at that time, linguistic insights can tell us how to generalize from little amount of data. And that's one thing. And the other thing it tells us is how to create natural-like data sets. So when you don't have data, either you need to create data or learn from little data. And in both the cases, linguistic insights is really helpful. To take an example, if you think of warfare, right, all through the history of humankind, and even in our mythology, you'd see that when you are fighting an army which is much stronger than you need war tactics, strategies, and you can still beat that big army. But if you really are on the other side, that is, I have really a big army, I seldom think of war tactics. Then what I think about is how to organize my army better, how to mobilize my army better. So I become more inward looking. So I look inside my model, how to scale them up, and how to train them faster and all that. But when you don't have that luxury of so much data or big army, you need to rely on external sources. What kind of external sources? How the landscape looks like. How can I take the enemy by surprise, right? So similarly, what kind of insight I can have from users? Can I use interaction as an approach? Can I, generate data through some tricks and tips and so on, right? So this is the central theme of this talk. And I'm going to illustrate it with a problem which I have and our group has spent quite a lot of time working, 10 years actually, which is code mixing or code switching. Code mixing refers to mixing of two or more languages in a single conversation, sometimes even in a single utterance. And we in India, most people do it all the time. Between Hindi and English, we mix and all that. So it's very common. All of you would be extremely familiar with this. But it's not only in India. Code mixing happens across the globe, right? So here are examples of tweets taken from various parts of the world. And you see various different kinds of languages are mixed. This top one here is actually Turkish and German. This is French and Arabic. I think this is English and Spanish, so on and so forth. So it happens all over the world. Various kinds of languages are mixed. And let me give you a little bit of more context to tell you why this is important before we get into the problem. So think of a multilingual society, like the one in which we live in India. So there are multiple languages which are spoken, and everybody are speaking the same set of languages all the time. So when that happens, right, there is a stable multilingualism. People are talking about the same set of languages. What happens is there are various kinds of interactions that happen between the languages. Okay, so one of the interactions is code switching, but that's not the only interaction. So you might have multilingual discourse. Somebody gives an entire talk in English followed by the same talk in Hindi so that it's accessible to all. So that's a multilingual discourse, but not necessarily mixing. On the other hand, you take words from the other language and use it. So there are lots of English words in Hindi, or lots of Bengali, Hindi, other Indian language words in, let's say, Indian English especially. So these are the two extremes. In between, there are all sorts of things, and code mixing is what we are going to look at. Why code mixing is interesting and challenging compared to these two extremes is that if it's a multilingual discourse, you separate by language and separately process, most of the time you are fine. If it's, borrowing of syntactic structures or words in a language from another, you don't even have to treat it as a different problem. It's a monolingual processing. You just have to collect data in the right way. But when you have code mixing, you cannot avoid the problem that's staring at your face, that there are multiple languages which are being mixed at syntactic level, at semantic level, at lexical level, at all levels. And somehow you have to process it. And, many of you might already know it's very intuitive, and we have showed it through a series of work that the monolingual techniques typically fail to solve the code mixing problems. So if you were to build an NLP system for a multilingual society like in India, you have to tackle code mixing, and the current technology is, I'm talking of, let's say, 10 years ago, that technology was very poor. Things have changed recently, and that's the interesting bit which I will emphasize in this talk. Now, a little more about the context. So it's very common to, by the way, if you look at Twitter, 3.5% of the tweets, actually, there's a lower limit. It's probably a little more than this, are code switched. And note that there is no incentive for code switching on Twitter because it's a broadcasting medium, but still people code switch. And it varies by geography, as I already said. So some places like, Paris, I think Istanbul, you have a heavy amount of code switching. We observe some 13%, 10% of the tweets are code switched. This is, by the way, Twitter statistics. So I'm not talking of how much code switching people do in day-to-day life. On the other hand, places like Houston, San Francisco has less, let's say 1%, 2%. Nevertheless, it's everywhere. We could not find a city where there is no code switching. So it's a pervasive problem. It's a major problem. Pervasive phenomenon, major phenomenon, and it requires to be handled. So if this is the case, right, it's pervasive, it's everywhere, people do it all the time, then where the problem of data comes from? There should be a lot of data, right? But that's the paradox of code mixed data that I'm going to talk about. See, code mixing is predominantly a spoken language phenomenon. So people mix language mostly when they're talking. Now, therefore, you really don't have Wikipedia, which is code mixed, books which are code mixed. You can crawl the web, but most of the data will be monolingual, right? Not code mixed. And speech corpus is harder to get. Then what do you do? Where do you look at for data? So then you could think of, Twitter, social media, or in general, other kinds of user-generated content on the web. They might be code mixed because people typically tend to write as they speak in some of the social media platforms. So that's there. But the problem is, there are massive privacy concerns. You can't just go and scrape the data and start working on it. And even if somebody can, definitely you can't share it publicly for the research community. This third problem is automatic detection of code mixing is very difficult. So the data doesn't come up with a meta label, right? That I'm code mixed. So you have to first identify if the data is code mixed. And for that, I mean, monolingual language detection is reasonably easy, even though that's also not fully solved. But code mixing is much harder to detect. And of course, like any other data collection problem, labeling is expensive. If you want to get labeled data for, let's say, sentiment analysis for code switching, natural language inferencing for code switching, that's going to be expensive. One extra dimension of this expense adds when code switching. That is that now you. So suppose I want to get Dutch and Turkish data annotated for sentiment. Where am I going to get an annotators for? In fact, we tried that, and Mechanical Turk doesn't help. It's very hard to get people who know a couple of languages and equally proficiently. So it's kind of a hard problem. So we have been, as I said, looking at this problem for last 10 years or so under these ages of Project Melange. There are a lot of my colleagues. I have put many and many interns, research fellows have worked over the years. Too many of them to read out their names, but they have a lot of contribution, and all the stuff that I'm going to talk about are their work. But I specifically want to call out Kalika, Bali, and Sunena, who three of us work in this Project Melange, have been working in this Project Melange since the inception. I would also like to call out a lot of external collaborators, especially in IIT Kharagpur, right in Loy. We have worked together on quite a bit of problems on code mixing. Right now I'm working with some of the people from IIIT Hyderabad. So a lot of contribution from a lot of people are here. And Microsoft has a new research institute set up in Africa. It's called MARI in Kenya. And we are working with them to look at code mixing in African languages like Swahili and English. And there are lots of languages, Sheng and so on. It's also a very fascinating space. Now, I don't have time, and neither I intend to go into all the work that we have done over the years, right? But I just want to set the context of what I want to come to, right? That we need to generate data because there is not enough data. I want to say what all the different kinds of models you can think about when you are solving code switching. One is you could think of code mixed data as a monolingual corpus and treat it as you do a monolingual corpus, right? It would work. But then there is a data explosion problem. For every pair of languages that is code mixed, you have to collect separate data and large amounts of data. If you are trying to build a GPT-3 for Hindi English code mixing, imagine the data you would need, right? The other way is to split it. So split into languages and then separately treat the languages. As I said, it works well when the languages are not mixed quite often. So like multilingual discourse, but when it is all mixed, like in code mixing or code switching, this doesn't work very well. And there are some other methods where you simultaneously process this using models of both the languages and finally put a combination logic and things like that. They work to some extent. Actually, along this line, this is the best model, but can we do better is the question. If you want to find anything about all the stuff, so this is what all we did till 2018, and now the situation is going to change. So if you want to find anything about all this work, I have put all these resources. There is a tutorial that we did, pretty extensive one and all. So I'll leave the slides with the organizers so you can get access to all this. Now coming to what happened in 2018, 2019. We had Ember. What is Ember? So we are now talking of this massively multilingual zero-shot learning. It's also called zero-shot cross-lingual transfer. The phenomenon is sometimes referred to. I'm not getting into the details because I know all of you or a lot of you are aware of this. So what happens is you have a BERT-like model, a transformer-based language model, which instead of one language, you train with multiple languages. These are all monolingual corpora. So English monolingual corpus, Hindi, French, Swahili, and so on, maybe hundreds of them. You train and you get a massive model, let's call it Ember. And then when you are trying to build a task on top of it, you just train a few layers for with task-specific data for just one language, let's say, or a few languages. So I want to build a sentiment analyzer. I just train it with label sentiment data for English, which is pretty commonly, I mean, usually English is the language where data is more readily available. But what's interesting is now these models start working for all the languages, albeit to various degrees. So cross-lingual zero-shot transfer is very lossy or noisy, depends on a lot of factors, but it does, transfer across languages reasonably well. So this is what is the magic of what is called the cross-lingual zero-shot transfer or zero-shot learning. So the question then we can ask is, now that we have Ember, and by the way, Ember was the first one, we have much better models now, like XLM Roboter was better than Ember, and there are even like multilingual T5 and other models coming up. There is Turing, the Microsoft's multilingual model, and so on. Now, these are even more powerful. So one question is, this multilingual zero-shot transfer, what it means is your model kind of knows all the languages, right? In some sense, it's able to process data across these languages. So then shouldn't it be automatically able to process code-mixed data? So if my model like this Ember already supports English and Hindi and Spanish, it should be able to support, let's say, by the same logic, right? So this is the thing that we wanted to test first, that is it true? So more specifically, I have this massively multilingual pre-trained model on unlabeled data from L1 to Ln, and I now fine-tune it on data from task data for only one language, L1, and I want to check if it can actually now process L1, L2 code mix data. And by the way, I mean, I might also want to check L2, L3 code mix data. It doesn't have to be like one of pivot languages. So this is the setup, experiment that I want to try. But if you want to try any such experiments, first you need, again, data. Now we need test benches, test data. And this has to be labeled, right? So as I said, it's very hard to get labeled data. Fortunately, over the last 10 years, again, people have built these data sets through part of various shared tasks. So there is a computational processing of code mixing series of workshop. As a part of that shared task, some data was created. There are similar shared tasks in India as a part of ICON, which is happening right now, another conference, then FIRE, Forum for IR Evaluation. So people have created these test benches. So what we did is we thought, okay, can we create a data set like glue-like data set? Let's call it glucose, glue for code switching. So this is a data set, by the way, built upon data sets which are already created by other people. So we just combined them and benchmarked it, plus included a few of the data sets that we ourselves built. At the same time, similarly, there is another data set which came up, which is called Lindsay from another group. And this is also a very useful data set. There's an interesting difference between the two, which one should remember, which is the glucose idea was that let's take few language pairs. So English, Hindi, and English, Spanish were the chosen languages because most of the data sets are there, and have a large number of tasks across those languages, starting from, let's say, LID, which is a very basic task, all the way to NLI, natural language inferencing, which is our question answering, which are higher level tasks. Similarly, whatever was available for Spanish, we did that. On the other hand, Lindsay actually goes language wise. So as many languages. So they have fewer tasks, but more languages. So one interesting thing to note is look at this last column. It shows how many total instances were there, right? And you see the numbers seldom goes beyond few thousand, right? There are only few tasks. One is the sentiment analysis for English, Hindi, and then this is, LID, language identification for Spanish English, and this is named entity recognition for Spanish English, which had tens of thousands. actually just like 110,000 or so on, but nothing more than that. So data is still an issue. Now, when we do the vanilla Ember, we just run the vanilla Ember, fine-tuning it on the task data for English. What do we observe? So this is interesting. In some cases, we also do, by the way, few shot learning on this training part of the code switch data. So that also in some of the cases we do. Anyway, so what we observe is this first column that you see is the SOTA, state of the art, before 2018. So how this SOTA was obtained was, those were the era of word2vec, and we were talking of cross-lingual embeddings. So cross-lingual embeddings using word2vec, and with that kind of SOTA, and actually a lot of other things on top of it. I'm not getting into the details, which people tried. These were the numbers we got, and these are the Ember numbers, where nothing more was done actually on top of Ember. So it just almost came for free. We didn't do anything extra for code switching. And look at the numbers, right? I mean, everywhere it beat the SOTA, existing SOTA. Not only that, you had big jumps at places like let's say 77% to 87% for post tagging, or let's say 89% to 93% is a pretty reasonable jump again for English, Spanish, and so on. So that's one observation, that it did very well. So our intuition is right, it works. But there is one more thing. Note the absolute accuracies, right? Are these good enough? NLI 60%, post tagging on one particular data set 60%, sentiment analysis 58%, same for Spanish 66% sentiment analysis. Nowhere close to the monolingual performance that we get for English, for Hindi, for Spanish, right? Individually. So there is a huge room for improvement, and that is required. There is a need for improvement. Not only a room for improvement, there is a need for improvement. So what do we do? What can we do? So this was the model that we tried, right? And which beat the SOTA. Now, can we improve on top of that? So one idea is, there is a lot of work which talks about this continued pre-training for domain adaptation. When you are trying to adapt these language models, let's say BERT, for a particular domain, let's say biomedical domain or something, you train it a few more epochs with a lot of biomedical domain data. So we thought maybe we should do the same. Let's say L1, L2 code mixed data, and we are interested in L1, L2 code mixing. So I take a lot of this data, and these have to be unlabeled, by the way. So that's probably easier to get. We'll come to how easy it is to get. And then we train these models. I mean, do continued pre-training, and then we can, run the rest of the pipeline as is. Or we could do continued pre-training and fine-tuning with little bit of code mixed data, like I already mentioned. We could do both actually. So both is what I'm going to report in the next set of results. What happens when you do L1, L2 code mixed data pre-training, continued pre-training, plus some fine-tuning with code mixed data. Before I tell you the results, where do we get the data from, right? So now I need unlabeled data. As I said, ideally transcribed conversational speech is the best kind of data that we can hope for. Most natural code mixed data. And this is what some of the data sets that are available. This is a little dated. I mean, 2019, I think a few more data sets would have come in between, but nevertheless, the state hasn't changed significantly. And you see the size, right? 54 conversations. And if you know, for you to move the needle, because Ember or XLM Roberta is already trained on billions of tokens. To move, I mean, make it a little better, you at least need millions of tokens, right? If not billions of tokens from the domain. So this own too. Next best is text-based chat logs, like I again already mentioned, WhatsApp, Facebook conversations, Twitter conversations, etc. But I said there were privacy concerns. Getting large amount of data is a problem there. Twitter is still okay, but WhatsApp and Facebook definitely has a problem there. You could go to non-conversational data, like Twitter is mostly non-conversational. You could go to YouTube comments, Reddit comments, a lot of people have used them. Since these are non-conversational, the amount of code switching, the type is slightly bad. But at the end, this is the best real code mix data that we have, and that's what we are going to use, by the way. So we'll call this real code mix data. So let's say English in the mixed tweets. And there are some other kinds of data sets also which are interesting. We did a lot of work like movie scripts. Bollywood features a lot of code mixing these days. So you could look at Bollywood movie scripts, which are freely, which are available readily online. But these are also small, not really extensive, not in the order of millions, nowhere close to that. Okay, so some bit of real CodeMixed data can be scraped from Twitter, let's say, or Reddit or YouTube comments, but that's not enough to move the. I will. Trust me here. I don't have the numbers for that, but if you just train with that data, do continued pre-training, it doesn't move the needle because you need a lot more data. What can you do? The question is, then can we generate artificially code-mixed data? So one immediate thought could be like this, right? I take an English sentence, randomly switch some words to Hindi, or or vice versa. Or maybe I take some random English phrases and random Hindi phrases and put them together. Would it be okay? By the way, a lot of people have tried this. So people did try that, and sometimes that also shows a little bit of improvement. But that's clearly that's not natural. Here is a motivating example. Consider this English sentence: teacher has issued a book from the library for the student. And I'm assuming most of you know Hindi. Sorry if you don't know. So there are two sentences, right? Teacher ne library se student ke liye book issue ki, and teacher ne has issued library se student ke liye book. And if I ask you which one of these two is more natural, almost most bilingual, every bilingual Hindi English speaker says the first one. The first one is a very natural sentence: teacher ne library se student ke liye book issue ki. The second one, most of them say unnatural. Some of them even don't accept. They say, no, this is not grammatical. I'll give you two more examples. I will go tomorrow. So that's the meaning of the sentence. And I'm code mixing it as I kal jaunga. How does it sound? Or main kal will go. How does it sound, right? Nobody will say this. Now, what is the linguistic constraint that we are talking about? If we can figure that out, maybe we can generate very natural looking code mixed data, which looks like the first sentence here and not like the second one. So fortunately, linguists have worked on these problems for a long time, starting all the way from 1950s. There are tons and tons of theories, books written on it, but there are few theories. So people don't agree on the theory. So there are some 4 or 5 different theories. Interesting thing is all these theories start with similar kind of assumptions. So they start with a pair of aligned parallel sentences, and most of these theories are syntactic, so they require a parse tree. So if you have a aligned pair of sentences, and if you have parse trees, then you should be able to apply these theories. You could build models of these theories and implement them. So that's what we did. We tried implementing some of these models. Now for translation, we could use available translators like Bing, and you could also use available parallel data if there is a parallel corpus. And for parse trees, what we did for the English side, things are easy. There are very good parsers for English. You parse the English side and project it onto the other side, because these theories also require, alignable parse trees. So you have to you can project. So that sort of works for a lot of sentences. Okay. Now, I'm not going into the details of the theories because I don't have time. They are pretty fascinating, but I will give you a flavor of what these theories are and why, some of the previous examples that I showed just doesn't work. So let's say I have this sentence. She lives in a White House. The Spanish of this is Ella vive en una casa blanca. So in a White House, if you see, is equivalent of en una casa blanca. So what this says is, suppose you take the Spanish syntactic tree the syntactic tree for the Spanish sentence, and just replace this PP, prepositional phrase in Spanish by the prepositional phrase in English, the equivalent one, and you get a sentence like this: Ella vive in a White House, and that is a good code mix sentence. So if you can define syntactic transformations like this, that generates good sentences. Whenever you violate these rules, it generates bad sentences. There are more rules to it. For instance, you cannot do multiple switching. For instance, once you have switched this, you can't again switch white to blanca. So you can't say Ella vive in a blanca house. That is bad code mixing. Similarly, there are certain words which cannot be switched unless the whole phrase is switched. So in cannot be switched independently without switching this phrase, and so on and so forth. Pronouns cannot be switched. So there is a bunch of rules which linguists have worked out. And I just want to tell you that we tried a lot of these theories and modeled them and even tested them, with human judgment, which of the theories explain which of these languages. And what we found is matrix language theory is a little more, seems like a little more accurate for languages like English, Hindi. For Spanish, English kind of code mixing, where word order is more similar to each other, a lot of these theories are equally good. But when the word order is very different, like in English, Hindi, matrix language theory seems to generate better examples. That's an aside. We have some recent work on this. Yeah, but now again, back to the main storyline. So the problem here is when you are generating the sentences, right, from a aligned pair, there's a combinatorial explosion. Because you see, I could swap this NP, I could swap this, I could swap this, I could swap a combination of them and so on. So this gives a combinatorial explosion. So if a sentence has, let's say, 18 words, it almost generates 4,000 aligned pairs. Now, if you take all these sentences and do continued pre-training, what would happen? It just screws up the system completely. Why it screws up the system completely? Because you are completely ruining the natural distribution of sentences. For instance, if you do this, then the longer sentences become many, many times more probable than the shorter sentences in your model, which is very counterintuitive to what you see in a natural distribution. So that's not going to do. So we have to sample equal numbers from each, maybe 1, maybe 2, maybe 5, but not more than that. So we also empirically validated that, around 5 samples per sentence pair works, no matter what's the length. But how do you sample? And it matters. Random sample doesn't help, actually. So you have to, again, go back to what is natural. And there are many theories that we could apply here. One way to think about it is how frequently you switch between the languages. And as you would imagine, in natural conversations, people don't usually say teacher ne library se student ke liye book shuki. People don't make so many switches. So if you go with switch point based sampling, that gives you very good results, actually. There are other ways, like code mixing. Index is one measure of complexity. You could switch, sample based on that. There are more deeper things that one could do, syntactic and lexical signals and so on. So these are a little open-ended problems. So we haven't done any of these things. I mean, we have done some of these things, but haven't explored in detail. So this is an open area. But yeah, this is the thing. Number of switch point based sampling, that where we saw the maximal benefit. Okay, the last bit is training curriculum is also important. So when you are pre-training, so up to monolingual data is already trained, right? So this is the Ember that you take. So after that, when you are doing, so remember I said you do have some real code mixed data. So what happens, what works best is you do a few epochs of training with the synthetic code mixed data, and then finally one epoch with the real code mixed data. That gives you the best accuracies, actually. There are many supporting experiments for several languages and several tasks that we have seen here. Now, finally coming to the results, does it help? So first, so here, let me first explain that the English in the column now is for the Ember, so not the SOTA. We had already bitten the SOTA, so now it's the Ember, vanilla Ember result. And this is the modified Ember, what I just talked about with pre-training and all. Now, can we do, is it better, this right column better than the left one? Let's look at Spanish English, right? Every task we are doing better. However, the delta is not very high. 66 to 69 is okay, but 93.33 to 93.62 is almost comparable. So the delta is small. In Hindi, it's a little more complicated. Out of 7, 5 tasks we are doing good. Some like NER, we are doing pretty good, 4% better. However, some tasks like, here, QA, we are doing even a little worse. And in fact, if you look at the monolingual performance for some of these cases, you are also doing a little worse, which is not acceptable. Your model should not regress on monolingual performance, right? So somehow it's helping, but not to the extent that we would want it to. So that is the thing to remember. With the Hindi case, I can further explain you a little bit. The problem is Hindi in natural setting, when Hindi and English is code mixed and typed, it's often Romanized, not in Devanagari. You don't type Hindi in Devanagari, you Romanize, like the examples I was showing in Latin characters. So the problem is when we actually generate with Devanagari characters because we take parallel data. So parallel data is English is in Latin and Hindi is in Devanagari. And when you do generated code switch sentences, you have Latin Devanagari, Hindi remains in Devanagari. So there is a mismatch there as well. We tried doing something for that, but I think that's one factor which shows that Hindi we have a little kind of not a very systematic result like Spanish. But from both together, it's kind of clear that it's helping, but we can do better. And definitely the absolute scores are nowhere there. There's plenty of room for improvement and we should be able to do better. Now, what should we do, right? So I already talked through this. So we say that we see that continued pre-training is helping monolingual performance. There's a big gap from monolingual performance still. But what is interesting is with bigger and better multilingual models, like this was Ember. With XLM Robota, the deltas become even smaller. And when you go to Turing or MT5, your deltas become even smaller, sometimes no delta at all. So it's like, the models are already so good that you can't do much better with synthetically generated code mixed data. However, at the same time, there is room for improvement. So there is a big gap here, it seems. So what should we do, or how can what could be a solution? I'm not going to give a solution for this. This is a problem I'm going to leave you with. But before we end up, right, let me try to talk about this very interesting. I mean, personally, I find this question very interesting. What really happens to Ember when we do continued pre-training with CodeMixed data? We saw that it's helping for English, Spanish, even for English, Hindi. But what's happening? What is changing in Ember fundamentally? So there was this recent work we had. It's called Bertologico-Mix. Many of you might have read the book called Logico-Mix, fascinating book, graphic novel. You should, if you haven't, on computer science. So we made a pun on it. So Bertologico-Mix, when Bertology meets code mixing. So how do you check, what happens to BERT? There are two ways of checking it. One is, treating BERT as black box and doing probing. And second is looking inside Ember. So the paper describes a lot of experiments, but let me just tell you two interesting and insightful results. The first is a black box experiment. So when in the left graph, right, I take vanilla Ember without any pre-training. Here, fine-tuning actually means pre-training. So without any further continued pre-training with code mixing. And remember, I can generate multiple versions, code mix versions of the same sentence pair. So I'm putting, plotting, this is a TSNE plot of the embeddings of, so one color means they all come from the same base pair sentences. So ideally, they mean exactly the same, these points. But you see the points are scattered. Some pink points are here, some pink points are here. Some red points are here, some red points are here, and so on. What happens is when you do continued pre-training, you get very neat clusters. Somehow the model is better able to process code mixed inputs now. So all the blue points are together, all the red points are together. So that is a fundamental change happening. Now, what is interesting, this data is for English, Spanish, but I had done continued pre-training with English, Hindi. So we don't even need English, Spanish code mix data to bring out this character, even with any language, right? So it's getting code mixing as a phenomenon rather than a so-called domain adaptation. Like it's not only for English, Hindi, it's generalizing to any language pair. So that's what was fascinating, that yes, it is learning something interesting. Now the question then would be then, looking inside BERT and what is fundamentally changing there. It's very hard. We looked at lots of signals and stuff. And one thing which I think has some promise, holds some promise of what's happening is what we call responsivity of attention head to code mixing. I'll explain in a bit. So there are 12 layers on BERT in BERT that we used and another 12 attention heads, right? So 12 cross 12, each means an attention head from a layer. So that's this heat map. And there are 4 experimental conditions. This is vanilla Ember. This is Ember with remember I told you lexical switching, just randomly switch some words. So this is that model. This is generated CodeMixed data. So Ember with continued pre-training with generated CodeMixed data. And this is real CodeMixed data. We are pre-training with real CodeMixed data. So there are 4 conditions. And this is the heat map of what? So we are plotting here responsivity. Responsivity is when each head, when my input is a CodeMixed sentence, what is the excitation of this particular attention head versus when it is not a CodeMixed sentence. So it is measured in an information gain sort of thing. So you can imagine, like, if I were to classify based on these attention weights, I were to classify whether the input was a CodeMixed sentence or not, this is the weight that a classifier will put on them. So that's how to think about it. So if you think of this plain vanilla Ember, right, there are these 2-3 heads which are paying a lot of attention to code mixing. Whenever there is code mixing, they just light up. But otherwise, it's not. The other things are all well distributed. Whereas if you see when you do these last 2, right, Ember and generated with Ember and plus real and Ember plus generated. So the highlights are much more distributed, as if more neurons or these attention heads are now paying attention, are now becoming sensitive to code switching. So it one way to argue that is when it is distributed, it is more robust feature, right? So now the system becomes much more robust to code switching. It understands, it can process code switching in a much more robust way. This right-hand curves actually show the same thing. It shows the distribution of the values of this graph or the heat map. So the wider the distribution, the more distributed it is, right? So you see here the distribution is peaky, and here it becomes more wider. So the effect of training with further continued pre-training with CodeMixed data makes it wider. So essentially, more heads become responsive to code mixing. So, but these are very early experiments, and I think there's a lot that we can do here. And finally, one last question we could ask is, since code mixing can impart so many interesting properties to these multi-language models, could code mixing then be used for training large-scale multilingual systems instead of or along with parallel data? Monolingual independent corpora. So this is again another avenue which is not very well explored, and I think people can look at it. So let me conclude. By saying a couple of things. First is, we already noted that there's a big gap between desirable and achievable performance for code mixed tasks. It still exists. It still exists with all the work that we did. We are improving, but it exists. Second is we need data. We need more data. And when I say this, it's not only monolingual data we need, but also code mixed data for most languages. Now, this is important. I'm emphasizing this monolingual data because the results I showed all were for English Hindi and English Spanish. Now we are working on English Swahili, and things are pathetic. The Ember accuracies are no better than a random classifier accuracy. So this was a work in ACL 2020 where we talked about how the resource is distributed across various languages in the world. And if you look at the 0, 1, 2 classes, they of languages, 88% of world's languages spoken very little digital presence and resources in even these massive models. So we really can't process anything using the modern techniques for these languages. Glucose and Lindsay are good, right? Test benches are good start. I think we need to expand on them because there is enough evidence. I mean, after a lot of experimentation, I think I strongly believe that these data sets are also skewed and biased depending on how people collected the data. Some of these data sets have certain kinds of sociolinguistic biases, some have syntactic biases, and so on and so forth. So we need more extensive and good test benches for code mixing. And last is, the topic of this talk, that linguistic techniques help in generating data, and there's a lot of scope for improvement here, because the sampling I talked about, for instance, was switch point based. I'm sure we can do much better if we, sample based on the lexical and semantic constraints people have. Just to give an example, drink, that word when used in a Hindi context, वो बहुत drink करता है, really means he's an alcoholic. Really doesn't. The interpretation can never be that this person drinks a lot of soft drink, right? So meaning changes when you do code mixing. So these things have to be captured by the models. We don't capture this. I mean, our models don't capture this. So of course, either you have a lot of data or you have better linguistic models. These are the two options that one has. Okay, so talk सुनने के लिए thank you again. And here is a small, advertisement. At MSR India, we are hiring at all levels. So researcher levels, engineers, and if you want to work on this kind of exciting problems in NLP and more broadly ML and AI, please, send emails to me or my colleagues or visit our website. Yeah, thank you.
Thank you very much for this interesting talk. I think we have a lot of questions here. So for the interest of time, I will just pick three. So the first one is, in constructing synthetic code-mixed data, can we make a simple assumption, say, Hindi speakers use English words as noun? Is there any existing work on this? That is, which pause tag is commonly code switched?
Yeah, so intuitively Hindi speakers, or not only Hindi speakers, intuitively when a pair of languages are code switched, nouns are the first categories which are changed to the other language. A verb comes much later and there are more constraints on verbs. However, adverbs also get code switched very often, and discourse markers get code switched very often. So you would have heard, I was telling him ki don't come here. So here that key is a discourse connector, equivalent of English that, right? And it's an extremely common thing that in Indian English people do. So nouns are common worldwide. Then there are language pair specific idiosyncrasies. We recently did a work on this with IIIT Hyderabad. I was working on this problem exactly. I can't tell more because that's under submission.
Yeah. Okay, so the next question is, I heard sentences like, wait, I will bhagao him, previously was unnatural to me, being normalized in the movies, etc. now. How do we define the rules when the forms of code mixing seem to be constantly evolving? Where do we draw the line?
Very interesting question, and whoever has asked, thanks for the question. So I remember I was looking at, like I told you, when we tried applying the linguistic theories, we saw that they don't explain a lot of phenomena that we are observing. So one of the theories, right, metrics language theory. So Professor Arvind Joshi, very well-known, researcher in the NLP and cognitive science community. So he had done one of the first papers, a parser for code switch languages using this matrix language theory. And I was telling him in one of the conferences that, look, Professor Joshi, some of these things that you have written in your paper doesn't hold anymore. I mean, I didn't say it doesn't hold anymore. I said doesn't hold, because this is what I observe. And his answer was exactly the same thing, that when I worked on it 20 years ago, code mixing was different. And today code mixing is different. In fact, code mixing varies by geography also. So in our lab, Kalika from Delhi has a much more, what should I say? She's much more open to this kind of constructs than, let's say, I am, because first of all, I'm not a native Hindi speaker, but I'm a near native Hindi speaker. But I have very low tolerance for this kind of, patawing, magawing, and all these kinds of constructs, because I haven't heard. So that also. So there is geographical variation and there is temporal variation, and that makes it very hard. We really don't want to draw lines. We want to serve everybody. And the question is then, how do you rapidly collect data and keep making your systems evolve as well?
Yeah. So the last question I will take, why are the languages clustering when the loss function actually is trying to use MLM loss on code mix data? Intuitively, it should go the opposite way, making the model less sensitive to the language and prioritizing more on semantics.
Right. So again, thanks for asking this question. I forgot to mention that we don't use contrastive loss here. So you were right. We only use MLM. We don't. If we had used contrastive loss, right, then we would have forced it to cluster. So we are not using contrastive loss. So we are just using MLM. Now somehow so this is my intuition. So when you take 5 sentences or 10 sentences which are generated from the same pair, the bulk of the sentence will look similar, right? And parts will be different. And when you do a MLM with these kind of things, the chances are that the model will learn more that they have the same semantics. So this is exactly what you mentioned. So it should go with more semantics, and that's what is happening. These sentences mean exactly the same thing, right? Semantically, they are identical. So it is getting better in semantics only, but along the dimension of code mixing also.
Okay, thank you very much for your talk.